My name is Allison Goodwell, and today I will talk about numerical methods from a basic programming perspective. Briefly, numerical methods allow us to solve difficult problems numerically or computationally using iteration. The type of problem that I'll focus on today is a differential equation with an initial condition. This involves a variable that's changing in time or space, and we have an equation for its derivative, and we know the starting point, which is its initial condition, and we are interested in its trajectory or its behavior over time or space. In a calculus or differential equations course that you may have experienced previously, you've probably treated these same types of problems analytically. However, you may have realized from these courses, or maybe not, that some equations cannot be solved analytically, and this is where a numerical method comes in handy. There are plenty of examples of initial value type of problems in civil engineering or other fields. One example is air pollution. So we might have a smokestack or a forest fire with a pollutant concentration, and we might want to know about the air quality 10 miles downwind. A second example could be in hydraulics. So say we build a reservoir that traps water and sediment, and we might want to know, how does the sediment build up over time in the reservoir? Or how does the slope of the river downstream actually change due to the reservoir? A third example could be in structures or materials, where we have a function for how heat propagates through a material and a temperature at which it will fail. So we might want to model the progression of heat through a material, or a fire through a building to analyze the stability of a large structure. So in all of these cases, we have some model equation and a starting point or an initial value, and a numerical method involves iteration or a multi-step automated approach to solve its trajectory. Conveniently, this ties in directly with programming concepts that you already know, such as loops and logical statements. So for these types of problems, we can write a relatively simple program to estimate their solution, and we have some control over how accurate our estimate actually is. The method I'll introduce today is called the Euler Method. The key to the Euler Method is that we replace the derivative in our model equation by a simple forward finite difference equation. This is a complicated way to say that we have dx dt, so we are just going to assume a time stepping type of problem here, and we replace it by this term. Here, I is going to indicate the index of the time point we are at, and delta t is a time step which we actually get to choose. If you think about it, this equation makes sense because the derivative is just the change in the variable, so dx, over the change in time, dt, and we are just using an approximation of these aspects to basically turn a calculus problem into algebra. So in terms of the simple forward finite difference, it's simple forward because we are dealing with the future. So we are dealing with time points I and I plus 1 instead of I and I minus 1, which we could have also done. And we are also only using two values of x, so it's pretty simple. Meanwhile, the finite difference indicates that we are turning a continuous problem, dx dt, into a finite or discrete approximation. So if you think about a derivative being this nice, smooth, continuous, curvy thing, what we are doing is approximating it based on a discrete time step, delta t. So we have this set up for the Euler method, and now I need to convince you that it's useful to solve your problem. Let's say that for our first time step, we start at I equals 1. So our equation now has terms x1, x2, and delta t, and dx dt, which is actually a function of x. So let's think about, what do we have? We have an initial condition, x1. We choose a time step, delta t, and we have an equation for dx dt that we can solve using the initial condition, x1. So what do we want? We want to know the future, or x2, which is xi plus 1. So that's perfect because we can just rearrange this equation to solve it for x2, which is our only unknown. So that's nice. Now we have x2, but now you might ask, how do we move on with our lives if what we really want is x at 100,000 time steps down the line? This is where the iteration or looping comes in. For example, you did this first step and you determined x of 2. Now we can act like this x of 2 is actually our new initial condition and use it to solve for x of 3. So instead of I being 1 and I plus 1 being 2, we now have I as 2 and I plus 1 as 3. Then we can use x3 to solve for x4, etc., all the way up until the time point of interest. If your problem is that you built a potato launcher and you want to know the trajectory of your potato and where your potato lands, your time point of interest would be the time at which the potato returns to the ground level. Note that you might not even know what this time point is offhand. All you have to do is iterate until you get to the point where you hit a certain condition. So for the potato launcher, the condition that you're interested in is when the future or I plus 1 height of your potato becomes less than 0, meaning that your potato hit the ground between time points I and I plus 1. Since we're talking about potatoes and projectiles in general, let's actually do this problem using the Euler method. The nice thing here is that we actually have an analytical solution thanks to physics, so we can compare how well the numerical method does compared to what we know should occur. So here's the setup. We shoot a potato projectile at an angle of 45 degrees from the ground with a velocity of 20 meters per second. Our questions might include, when and where does the potato hit the ground? First, let's set up some units. So we'll measure the time in seconds, the distance in meters, and the horizontal direction will be called x and the vertical direction will be y. We know our initial x and y position, so basically 0, 0. We know our initial velocity, and here we can see that this initial velocity can be broken down into initial x and initial y velocities. So something to keep in mind here is that gravity is acting in the y direction, as we know, so that's why we expect the potato to slow down and stop moving in the y direction before coming back down to the ground. Meanwhile, the velocity in the x direction is constant, but it's going to have to stop because it will hit the ground. First, I'm just going to pop up the analytical solution for the potato's y and x positions as a function of time. Here are the equations, which directly provide everything about the trajectory at any point in time, so you can just plug in time and solve for the trajectory. This plot shows how y varies with time. So we see that for these conditions that it hits a high point of about 10 meters, and it hits the ground as shown by the y equals 0 line at exactly 2.88 seconds. We can find this time specifically by asking the question, when does the y value start becoming negative, which is what I've done here in the code. We can also plot x over time and see that since the x velocity is constant, that this is actually linear. We can finally plot x versus y to actually show the trajectory of the potato in space. Here we see again that the top height is a little over 10 meters, and the potato hits the ground at about 40 meters in the x direction. Just for an illustration, this is what our trajectory would look like for a higher launch angle of 60 degrees. So here we see that our potato flies higher and for a longer time, but lands shorter in the x direction. Meanwhile, if we go back to the initial launch angle of 45 degrees, but then we decrease the velocity by half, we see that the potato lands more quickly and covers a lot less distance. This analytical solution for a projectile serves as a nice check for our Euler method. For the Euler method, let's just assume that we cannot solve directly for y of t and x of t like we did just now. Instead, all we know is the acceleration due to gravity, and we set up our Euler equations like this. And now we need to choose a time step. Based on what we already know, let's start with delta t is 0.5, which is really large since we know that the potato is only in the air for about 3.5 seconds. So this is really a case where we only expect to have about 7 iterations of the Euler method before the potato hits the ground. We initialize our x and y with our initial conditions, and we are now ready to iterate. Here I'm using a while loop in Matlab to iterate, which will end whenever the y value becomes negative, again indicating that the potato must have hit the ground. In this Euler solution, I'm actually using the Euler method to solve for the velocity in the y direction based on the change in velocity being the acceleration due to gravity, And then I'm solving for the x and y positions themselves, also using the Euler method. Finally, I'm going to plot my trajectories on top of the analytical solution plots just to see what happens and whether they're relatively similar. Just as a note, you could definitely take a crack at this by hand, especially given a large time step like 0.5 seconds for this case. However, let's use the power of a computational method since we have all the tools we need. So what happens? We see that in general, our Euler method does pretty well, but as it's a very coarse approximation, it obviously overestimates our known solution. So let's try a smaller dt of 0.25. We see that this one does a lot better and gets closer to the analytical trajectory, and we can decrease and decrease and decrease our delta t until we get all the way to about 0.01. And here we actually can't tell the difference between the Euler solution and the analytical one. However, we used a lot more computational power because there were so many iterations. This is something we won't address here, but it is very relevant for large programs where we might have tiny improvements in accuracy that might come with high computational costs. So there's sort of a trade-off involved. We also won't discuss the many other types of numerical methods that are more complex and can have a lot higher performance, but they all have this common theme of approximating a solution with numerical iterations.